Today's lecture is going to be destabilizing for you, I think, because we're going to throw doubt on the usual intuition that we have about the natural number system. We have this idea that the natural number system is a very uniform and regular arena for doing arithmetic. In fact, it's not at all so. Once we get to larger and larger numbers, almost everything that we know starts to break down and continues to break down further and further the more we go. This is very disconcerting and also sheds a lot of doubt on these grandiose claims that we are in possession of all natural numbers. That's complete nonsense. Okay, so what we've been talking about is the complexity of a natural number. It's a very powerful but relatively simple notion that captures how difficult it is to write down a given natural number, where we have various arithmetical operations at our disposal. So we had a look at the complexity which I called triangular complexity, which is a reasonably natural one, and we saw that very roughly we had a picture something like this. That if here is sort of the scale of natural numbers from 1 up to, say, 10 triangle 10, and my favorite z equals 10 triangle 10 plus 23 is just adjacent there, that the complexity of these numbers can be sort of visualized by a graph that looks very roughly something like this. Okay, so this is a very distorted, inaccurate, not to scale diagram. But the complexity of most of the numbers in here is roughly at the level of 10 triangle 9, a tower of tens, one less. And the complexity is rather chaotic or almost fractal-like. Most of the time it's hovering around here, I claim, and every so often it goes dipping down in a rather unpredictable fashion. So these dips going down here correspond to finding a number that can be expressed very efficiently. For example, say 10 triangle 8. Okay, 10 triangle 8 is a very, very compact number because we can write it down with 1, 2, 3, 4 symbols. 10 triangle 8. Its complexity is only 4. So this complexity function goes plummeting down almost to 0 for that particular number. But that's a big anomaly. That's not very unrepresentative of what typically happens. Typically, the complexity is up here. So we want to get at this phenomena, but a little bit more concretely and precisely. So we want to say some precise things today about complexity. And we're going to aim towards this claim that most numbers between 1 and z have complexity, well, at least bigger than 10 triangle 4. And so are ultimately really invisible to us. This is going to throw a lot of questions and doubt on a lot of things that we take for granted. Okay, so it's a rather heretical lecture today. But I think it's really a topic and a direction of thinking that ought to be much, much more well understood by mathematics students. What I'm going to be doing today is not that complicated. There's a bit of inequalities that we're going to have to work with, but they're not too hard. You'll see that the argument is relatively simple and, in fact, somewhat crude. But nevertheless, the consequences are very striking. So let's recall that if n is a natural number, that its complexity c of n, or more precisely its triangular complexity, c sub t of n, is the minimum number of symbols chosen from this collection of symbols for an arithmetical expression for n. And the symbols that we have at our disposal here are the digits 0 to 9, there's 10 of them, the plus sign, the multiplication sign, the exponentiation sign, the triangular sign that corresponds to our hyper operation of tower of exponents, one on top of the other, and our left bracket and right bracket for organizing things. So, for example, the complexity of 1001 is 4 because it requires 4 digits to write down, and that's the most efficient way of writing this thing down. However, C of 1024 happens to be 3, since we can write 1024 as 4 exponent 5, 4 to the 5. So there's only 3 symbols required for that particular number, so its complexity is 3. C of, what is this, 5,764,803 happens to be 5, since this number can be written as 7 to the 8 plus 2. So altogether we need 1, 2, 3, 4, 5 symbols. Its complexity is 5. This number here, which has quite a lot of more digits, 3, 6, 9, 12, 14 digits. So its complexity could be all the way up to 14, but we claim that it's probably 9, since we can write this number down as 5 times 3 triangle 3 plus 9 to the 9. And here we are using 1, 2, 3, 4, 5, 6, 7, 8, 9 symbols. Now, of course, what I did to get this is I wrote down this expression first, and then I evaluated it, and then now I'm claiming that the complexity is 9. And I'm not entirely sure about that. It might be possible to write this in a more compact way with some other combination of exponents and triangular powers, etc. Now, if I choose some somewhat random number like this one, which I think has 23 digits, then my guess is that its complexity is 23. So in this case, I've just written down randomly 23 digits. So it's a pretty good guess that its complexity is 23, but it's not entirely clear. And actually finding out whether that's the case or not is problematic. It's not so easy. Okay, so that's complexity, or triangular complexity, of a natural number, expressing how much work is required to write this number down in some efficient, clever way. So it's a little bit like a compression of images. If you have an image that you want to transfer over the internet, then if it has many, many pixels, then it might be quite a lot of information. And so it's useful to be able to compress these things. And that's sort of what we're doing here. It's kind of a compression of information using our arithmetical operations. But in this case, we're not interested in loss of information. So we actually want to compress our number without any loss of information. So we want to be able to recover completely the number from the arithmetical expression that we're considering. So we want to make some observations about complexity. And of course, finding the complexity C of n for a particular natural number n is rather difficult in general. But it turns out that we can make general statements in a simpler and easier fashion. So what we're going to be doing is using counting and estimation. Here are our bunch of symbols that we're using. There is 16 of them. Let's refer to that number as k. So there are k symbols at our disposal. And we're going to often just operate with k because later on we might want to augment these symbols, make k a little bit bigger. So although we're mostly interested in k equals 16, we'll often have general expressions involving k. And we're interested in using these symbols, as we've said, to create mathematical expressions like this one here. But we're also going to be interested in sort of more general considerations, where we're going to consider more general words that can be created from these symbols, not necessarily representing legitimate mathematical operations or expressions. Okay, so this we recognize as a legitimate mathematical expression. We could evaluate that to a natural number. This thing, on the other hand, looks a bit funny. It's not a proper mathematical expression. It's just sort of a random list of symbols from our symbol set. Nevertheless, it's going to be useful for us to consider these kinds of more general words because they're easier to count than these mathematical expressions. And so we lose some information. We're being less precise when we're talking about these general words, but nevertheless, that's enough for us to still be able to draw the conclusions that we want to draw. So let's ask some questions. First question might be, how many mathematical expressions can we form with our k equals 16 symbols which have length, say, capital M? How many mathematical expressions of length m can we make? Well, for us, that's too hard. Okay, that would be an entire theory and trying to figure out which combinations of symbols are valid mathematical expressions and which aren't. So that's too hard. So let's ask a simpler question. How many words of length m can we make with our 16 symbols? Okay, so that's relatively easy because it's just a counting problem exactly of the kind that we've talked about in this series relatively recently. It's in fact the first of our 4 fundamental counting problems. We're just counting the number of m lists from k. Because if we're talking about a word from these k symbols, well, it means that we're talking about a list. Okay, and this list has entries from k, well, from these k 16 symbols, and the total length of the list is m. So the number there is k to the m. We can have k choices for the first entry of our list, k choices for the second entry, all the way up to k choices for the mth entry. And so we have to multiply all those together. We get k to the m. These are the number of m lists from k. Or in other words, the number of possible words of length m, irrespective of whether they actually form valid arithmetical expressions or not. Okay, how about the number of words of length less than or equal to m? This is the number of words of length exactly m. So we have the case when the word length is, say, 0, in which case, say there's only one word, the empty word. If the m is equal to 1, then there are k such lists. If m is equal to 2, then there are k squared such lists, and so on, all the way up to m, where we have k to the m such lists. So we're just using this expression to sum from 0 to m of this expression. Now this is a geometric series. Okay, it's a geometric series with a sort of common ratio of k, and so there is a standard formula for that we've seen, and it's k to the m plus 1 minus 1 over k minus 1. So I remind you that k for us is actually 16, but we'll keep on using k for now. So this expression here, we can simplify it a little bit because this numerator is less than or equal to k to the m plus 1. If we just drop this minus 1, then we're making things a little bit bigger. We'll keep the denominator as it is. So this to this is a valid inequality. And now, just to make things a little bit easier as well, we're going to increase it again by, in this case, decreasing the denominator. So from here to here we increased the numerator. From here to here we're going to decrease the denominator. If we decrease the denominator, it means that the actual expression gets bigger. And we're going to decrease the denominator from k minus 1 to k over 2. So k is 16, k minus 1 is 15, k over 2 is down to about 8. Okay, so we're going from 15 to 8 in the denominator. That increases the expression overall. And the advantage in doing that is that now we can cancel a little bit because the 2 can come up there, and this k and one of the k's up here will cancel. So we'll just get 2 times k to the m. So this analysis shows that if we're interested in the number of words of length up to, including m, then it's less than or equal to 2 times k to the m, which is exactly 2 times what we got in that previous question. And now let's just state an obvious consequence of what we just done, which is that there are at most 2 times k to the m numbers n. Whenever I say number here, I'm talking about natural numbers, with complexity c of n less than or equal to m. Why? Well, there are at most 2 times k to the m words in the k symbols of length at most m. That's what we've just established. So that's a limit on the total number of words that we can make with our 16 or k symbols. So there are at most this number of arithmetical expressions in the case symbols of length less than or equal to m. Because an arithmetical expression is just a special kind of word. And so there are at most 2 times k to the m numbers, in natural numbers, of complexity c of n less than or equal to m. Because these arithmetical expressions that we've just counted up here correspond to, or evaluate to, natural numbers. And so there's at most 2 times k to the m such numbers of complexity less than or equal to m. So for example, there are at most 2 times 16 to the 500 numbers n of complexity c of n less than or equal to 500. We're interested in the number of numbers whose complexity is less than or equal to 500. So the numbers themselves could be very big, involving triangles and of triangles of triangles and so on. But the number of such numbers whose complexity is less than or equal to 500 is bounded by this number here. This is an upper limit to the number of mathematical expressions that we can make with our 16 symbols of total length less than or equal to 500. This is still a very big number, but we have some control over it. Now we're going to need another simple question. How many numbers have digit length less than or equal to n? And just to make the answer a little bit simpler, let's include 0 here in this counting. So we're talking about a certain number of digit lengths. It's capital N. How many numbers are there? The answer is 10 to the n, because in each of the digit places we can put one of our 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, or 8, or 9. Okay, and now we're in a position to ask the question that's really at the heart of this lecture. And that's this one here. What fraction of the numbers n with digit length less than or equal to n have complexity c of n less than or equal to m? So we're assuming we have 2 numbers, m and n, and we'll suppose that n is bigger than m. Okay, and we're asking, okay, how many numbers of size or digit length less than or equal to n have complexity which is at most m? So we're interested in sort of what proportion of all the numbers of length n can we compress efficiently using our arithmetical expressions involving our 16 symbols to have complexity actually less than or equal to this fixed m. Okay, so we're talking about a ratio here of numbers whose complexity is less than or equal to m divided by all of the numbers that we're considering. So the total number of numbers that we're considering is just the number of n whose total number of digits is less than or equal to n. That's just 10 to the n that we've just found. So that's the denominator of this expression. And the numerator is, well, the number of numbers with digit length less than or equal to n, which has complexity less than or equal to m. And we're going to observe that this condition of having digits n less than or equal to capital N can be removed. So if we remove this condition, we're increasing the number of numbers. We're increasing this numerator. So when we're going from here to here, what I'm doing is I'm just dropping this condition and we're just replacing it with this number of n such that the complexity of n is less than or equal to capital M. Right. So here we're no longer restricting ourselves to numbers of a digit length less than or equal to capital N. We're just considering all natural numbers that have this property. And we're doing that because we've just counted that in the previous slide. That was less than or equal to 2 times k to the m. So altogether, this fraction of numbers is some number which is less than or equal to 2 times k to the m over 10 to the n. And I remind you that for us, k is actually 16. But this argument would work even if k was something different, if k was 20 or 30 or something else. Let's have a look at an example. So suppose n is 20 and m is 10. So we're considering numbers with 20 digits or less, and we're interested in what proportion of all those numbers have complexity less than or equal to 10. Okay, then we've just seen that this proportion, whatever it is less than this number here. 2 times k to the m over 10 to the n. Now k is 16, m is 10, and capital N is 20. If we look at this for a second, we see that we can simplify it because 16 happens to be 4 squared. So this 16 to the 10 is the same as 4 to the 20. So we get 4 to the 20 over 10 to the 20. That's the same as 4 over 10 to the 20. Times 2, of course. And then we can simplify things a little bit more because we're only interested in rough estimates here. So the 4 over 10 is a little bit less than a half. So we can replace it with a half, and then things get bigger. If we replace it with a half, then we get 1 over 2 to the 20. So altogether 1 over 2 to the 19. So for example, here is a random number that I've just made up with 20 digits. So if we take a random number like this, we ask what's the probability that the complexity of this number is actually less than or equal to 10. Now we can write it in some fashion or another using multiplications, exponentials, and triangular numbers with a total of less than or equal to 10 symbols. So here we actually need 1, 2, 3, 4, 5, 6 for the exponent, which is sort of implicit here, but you actually need the exponent if you're going to write things out. Then 7, 8, 9, 10. So this number would have complexity 10. So we're stating that the probability of that happening is less than 1 in 2 to the 19. A very, very small probability. So to being able to compress a number of 20 digits to something only involving 10 symbols is highly unlikely, or highly difficult, highly improbable. So let's just generalize that last example. So when n was exactly 2 times m, then we saw there was some kind of nice relation that could be easily summarized. Then the proportion of numbers with less than or equal to capital N digits that can be compressed to have complexity less than or equal to m is at most, so here's our general expression, 2 times k to the m over 10 to the n. And we've seen we can write that as 2 times 16 to the m, now over 10 to the 2m because we're replacing n with 2m. Okay, the 16 to the m is the same as 4 to the 2m. And so we get 4 over 10 to the 2m, or the same as 2/5 to the n, because n equals 2m. And this is less than 2 times 1/2 to the n, same thing that we just did in the previous thing. And we get the same thing, the kind of thing that we just did. We get 1 over 2 to the capital N minus 1. So we have concluded the following relatively simple, relatively crude estimate, which is that the probability that a number of capital N digits can be compressed to half that number, in other words to m, which is n over 2, using our 16 symbols, is less than 1 over 2 to the capital N minus 1. So this is a special case when we're just interested in asking how likely is it to be able to compress to half the original size of the number. How likely is that? And the answer is, if n is large, it's not very likely. It's very difficult to compress a number which is this long to a number which is this long if we have lots and lots of digits. It's a huge compression that's very unlikely. This has very important ramifications for us in mathematics. So I'm inviting you to wake up to the reality of what's really happening here in modern mathematics in this series. I want you to open your eyes to seeing things the way they really are, not the way that we've been led to believe by repetition, habit, wishful thinking. what we're going to see now is a very important aspect of that the nature of the natural numbers is much more complicated than we think it is, and that even relatively small numbers in the vast pantheon of things like Z, 10 triangle 10 plus 23, poses huge problems for us. Huge problems. And all of our proofs and number theory statements, we start to realize become problematic once we get into this range. Okay, so what we're doing here has enormous implications for the validity of, or the extent of the validity of modern number theory, and a lot of other things too. So here's a bit of a pictorial summary of what we've just done, using our very rough and somewhat crude estimation of this complexity function. So maybe I should label these things. Here is our number n, and here, as usual, is our complexity, C of n. Okay, so we're plotting C of n as a function of n. And we're pretending that this is something of a linear scale. And so I have 10 triangle 10 here as this bounded rate. Adjacent to it is z equals 10 triangle 10 plus 23. Of course, if this was a linear scale, you wouldn't be able to tell the difference there. And I'm also cheating in that I've identified 10 triangle 4, which is kind of a nice number for us, and sort of made it a lot bigger than it actually ought to appear. And on this scale here, we have 10 triangle n up here, which will be the rough complexity of most of these numbers in here. And I'm claiming that this complexity graph looks very roughly something like this, that most of the time it hovers around here and every so often it plummets down dramatically. Okay, now what we have just learned is the following, that if we call this number capital N, so this is representing the number of digits of the numbers that we're considering, and half of that is, say, m. That's just literally half of that number. So in the large scheme of things, there's not much difference between these two things, because, for example, 10 triangle 8 would be far below them. But anyway, let's picture m as roughly half there in that green line there. Then what we've just determined is that the probability of taking some number in this range and getting a complexity which is less than or equal to m, that's the halfway point, that probability is something like 1 over 2 to the 10 triangle n. 10 triangle n is the number n. Actually, there was a minus 1 here, wasn't there? But we're going to forget about that minus 1. Okay, so the basic point is that the probability of choosing something in here and getting a complexity even below this absurdly huge number is absurdly small. This is a ridiculously small probability. So the chances of this happening are, 0.00000000. I'd have to go on for quadzillions of quadzillions of quadzillions of universe eras before I even got close to where I could put something non-zero in that expression. So the conclusion is that most numbers now in quotes, notice I'm putting them in quotes now, most numbers less than z cannot be written down in our universe with our 16 symbols. If we just restrict ourselves to the 16 symbols that we have at hand and ask ourselves, which of these numbers can we actually write down? Because our visible universe, as I'm going to talk about more in my next lecture, is it's a small band here, maybe around 10 triangle 4 if we're lucky. Far below 10 triangle 9 over 2. So in other words, the number of numbers whose complexity comes down into our visible range is just a minuscule proportion of all of these numbers. When we bump into something like 10 triangle 8 or 10 triangle 8 plus 3,495, that's an absurdly special, remarkable number, totally atypical of the vast majority of them, which are invisible to us. Now this raises a lot of serious questions, people. Okay, if a number is invisible to us, if we cannot write it down in any fashion whatsoever, well, here we're not talking about any fashion whatsoever. We're talking about just using these particular 16 symbols. But in our next lecture, we're going to see that basically this argument extends quite simply to a more general situation. We're going to really run into this problem of the nature of numbers themselves. We're going to have to reconsider what we actually mean by a number. Is it right to talk about some number in this range which we have no hope of writing down in our universe? Is that really a number? All kinds of interesting scientific questions arise here, maybe also philosophical ones. But in any case, the framework of number theory, of our usual arithmetic, of our standard orientation is shaken up considerably by this kind of relatively simple analysis. It's an analysis that should be much more commonly known and shown to students because, first of all, it's interesting. It relates to sort of computational issues quite directly and obviously. It relates to notions of compression and science, and as we'll see in our next video, to actually considerations about the size of the universe. The question of how big the universe is starts to impact with what we can write down mathematically, and so perhaps what we are capable of theorizing about mathematically. So I want to talk a little bit about that in our next video. Hope you'll join me for that. I'm Norman Waldberger. Thanks for listening.